Hi, this is Travis with Kaiser, and today I'm going to talk through a somewhat general view about some particle physics and how our HVAC systems interact with them. I'm recording this in April of 2020, which means that COVID-19 is happening, but I promise I'm not going to say COVID-19 until the very last slide of this thing. First up, when we cough or sneeze or talk, we produce particles. They're mostly water. If you've ever cleaned your glasses by exhaling on them, then you probably know that. You breathe out on your glasses, and then they fog up and you clean them. The water in exhaled breath is in tiny water droplets. They vary in size between 5 and 100 micrometers, which is very small. There's 1,000 micrometers in a millimeter. But for what we're going to talk about today, we're going to say that 10 micrometers is big. If someone is sick, some of those water droplets will have pathogenic microbe particles inside them. Those microbe particles themselves are much smaller. Viruses can be as small as 0.1 or 0.3 micrometers. And so when there's a biological particle inside the water droplet, we call that a droplet nuclei. In some diseases like tuberculosis, those droplets evaporate and expel the droplet nuclei. And when that happens, then the virus, the raw virus, not surrounded by water, is in the air. So we call that an airborne or an aerosol. And that's really all I'm going to say about the biology side. From here on out, we'll talk about particle physics and HVAC. First up, we have the law of gravity. Gravity acts to pull particles towards the ground or whatever surface is between them and the ground. So we call that settling. Different particle sizes have different settling rates. That can be determined by an equation called the Stokes equation, but there's also plenty of sources out there where they've been published in tables. The bottom line from my table in blue up at the top of this slide, and reading from right to left, the larger particles will fall 5 feet in about a minute. The 4 to 20 minutes for those 10 to 20 micron particles. 5 to 10 micron particles might take 45 minutes to hit the ground. At a certain point, the force of gravity and the air resistance are essentially, they balance each other out. So those particles fall very, very slowly. In practical terms, we consider them to be suspended in the air. One gigantic word of caution about these settling times is that they assume zero initial momentum. In practice, that's almost never going to be the case. Even when you're just breathing or talking, the droplets or the water droplets that come out of your mouth are going to have some initial velocity. The air velocity of a normal human exhalation is between 400 feet per minute and 1,500 feet per minute. So now if we want to take an HVAC system and deliberately move particles from one place to another, we need to talk about capture velocity. This concept is pretty simple. In order to move a particle, we need to have a certain velocity in the air to pick it up and move it. If those particles don't have any initial momentum, then that's not much. 50 to 100 feet per minute will do it. But in healthcare, at least, zero initial momentum is going to be false. That's an incorrect assumption. The air velocity of the normal human exhalation, again, 400 feet per minute up to 1,700 feet per minute. There are some crazy numbers out there about particles and sneezes moving at 100 miles an hour, which is 9,000 feet per minute. I don't know if that's true. But I do know that when you want to capture a particle that has some initial momentum, you need more capture velocity. And so that's when we see numbers of 500 or 1,000 feet per minute in order to guarantee that we're going to pick that particle up and move it. Momentum, by the way, in physics, the variable capital M, momentum, is defined as mass times velocity. So a 20 micron droplet or particle moving at the same speed as a 10 micron droplet or particle has twice the momentum. Okay, so now with some basics physics down, let's start talking about HVAC and some measures that we might use. First up is local exhaust ventilation. The smartest thing we can do is to capture particles where we know they're being generated. This is what we do in labs, this is what we do with fume hoods, this is what we do with biosafety hoods. We do this quite a bit in manufacturing and industry, in a lot of applications. We do this in our scope cleaning rooms. So you can use local exhaust ventilation for gases, vapors, fibers, mists, fumes, dust. And we usually send them to some sort of cleaner to remove those contaminants at that point, or just exhaust them and get rid of them. There's all kinds of different configurations for local exhaust. You have snorkels and hoods and downdraft hoods and side draft hoods and canopy hoods and boots and enclosures. The list goes on and on. The picture off to the right is a novel concept introduced in 2017 by Dr. Ken Mead at CDC. That's called headboard ventilation, where we put a capture hood basically above the source when the source is a patient. Okay, let's talk about basic room ventilation. For an airborne particle, a very small particle, we consider that essentially to be mixed into the air, which is to say that we basically consider that it obeys the ideal gas law. When we say 10 particles per cubic meter, we treat that as though there are in fact 10 particles equally spaced out throughout that cubic meter. And for that condition, we can use dilution ventilation. Dilution ventilation is a logarithm. So you bring in uncontaminated air to dilute the contaminant. The logarithm means that there's a diminishing marginal return. So a poorly ventilated room will have a high concentration of contaminants. You'll see a massive benefit to bringing in 1 or 2 air changes of dilution ventilation. You'll see about half of that benefit to go from 2 up to about 6 air changes. And then beyond that, the benefit drops off, quite a bit. The recommendation for airborne isolation rooms in the US since 1994 is 6 air changes per hour for existing buildings and 12 air changes per hour for new construction. Internationally, that number circles around 6 air changes per hour. The graphics on the right come from our typical HVAC room comfort literature. The air in a normal, comfortable room does not have a lot of velocity. In fact, we're deliberately trying to avoid that. The goal is to mix air and achieve an average room velocity of 20 feet per minute or less. The reason being, velocity in the air is uncomfortable. If you had 50 or 75 feet per minute of average velocity in a room, then the occupants would be cold and they would complain. So we generally don't have that. And that's kind of an important point. When we talk about larger particles or droplets, the room ventilation itself is not going to do much of anything. We are not going to pick up those large particles and move them. At least we're not going to do it on purpose because we just don't have anywhere near the capture velocity that we talked about 2 slides ago. So we may get some large particles up in the ducts by accident, or if they get directly coughed or sneezed up there, but our room ventilation is not really a meaningful tool to affect larger particles. Smaller particles, yeah, fine, but not larger particles. So what about 100% outside air? That's very common in Europe. It's not so common in the United States, although some of our systems have economizers or they can be converted to 100% outside air, weather permitting. I've encouraged engineers to think about this in terms of dilution factor. It's kind of a simplistic idea, but I found it to be very useful when talking to our clinicians. And I try to key it to the human breath. The human breath is about 0.2 CFM, cubic feet per minute, and that's 12 breaths per minute with a half a liter lung capacity. If you have a patient on a non-invasive breathing apparatus like a CPAP, that ventilator could be doing up to 1.5 CFM or 40 liters a minute if you're a respiratory therapist. So anything that we do in our HVAC system provides dilution to that air. The room ventilation dilution dilutes the air, but on a common system, the air from the room next door also dilutes the air from the storage rooms or the hallways or anywhere else. It's all dilution air. So if you're dealing with an air handler that has 5,000 CFM of return air, the dilution factor to a human breath is going to be 30,000 to 1. To a breathing machine is going to be 3,000 to 1, right? And if you add filters into the mix, they can remove a bunch more particles. The reason I like talking about dilution factor is that it seems to be understandable. In the isolation rooms, the 6 air change or 12 air change isolation rooms that we do, we normally dilute the air in the room to a factor of about 150 or 300 to 1. And so it makes sense that once we can get into a system where we see a dilution factor of 1,000 to 1 or 3,000 to 1 or more than that, then we've done our job. We've diluted that contaminant. We're probably not going to do a whole lot more good aside from that. Okay, let's talk about filters. There's been a lot of talk about HEPA filters here in the last 3 to 5 weeks. We usually design air across filters for about 400 feet per minute to 600 feet per minute. So most of the units that you see pictured here are somewhere between 600 and 2500 CFM. In a normal patient room, that can be a lot of ventilation. It's some capture velocity, but not a ton of capture velocity that you'll see at the inlet there. Now, there's some misinformation out there about HEPA filters. Since HEPA filters are only rated down to 0.3 micron, I've heard it said that, hey, a 0.1 micron particle could fly right through that, and that is false. There have been tests on that. If you need the analogy, imagine a very small fly trying to fly through a bug screen, and of course, he'll make it through, no problem. But if you imagine that same fly trying to fly through, 100 million bug screens, one right after the other, and all misaligned, and he's flying at full speed, unless he's Han Solo, he's going to crash at some point along the way. Almost always going to crash at some point along the way. That phenomenon in filters is what we call Brownian motion, and it's pretty well documented. So for small airborne particles, HEPA filtration is great. The air leaving the HEPA filter should be considered clean. It's 99.97% free of particles. Or if you like the dilution factor concept from the last slide, that would be a dilution factor of 3,300 to 1, which is very, very clean. For droplets or larger particles, things like this, units like this are going to have a very limited effect because you need a capture velocity in order to drag that particle through the filter. If you can get the particle to the filter will most certainly catch it. But the inlet velocity here is very, very local. So if you have a large particle that moves right in front of the inlet, it might get caught. But if you're falling even just a foot away from the inlet of this thing, it's probably not going to drag a large particle into the filter. One other thing about HEPA filters, which leads me to a little bit of criticism. The air that comes out of a HEPA filter is clean. It's 99.97% free of particles. These diagrams are some of what Ashray and Ashy put out in March of 2020. And they were talking about using these HEPA fan units for negative pressure, which I will talk about in a few minutes. But if you're going to clean the air, please don't waste it. The top diagram here shows taking a HEPA filter, cleaning the air, and then dumping it outside, which in my mind is a waste of clean air. The second diagram here shows cleaning the air, then putting it back to the system. Well, the system is already going to dilute the air, so that's not a terribly good use of an air cleaner. The third diagram here shows clean air discharging in the room, and that's great because now you've actually cleaned the air in the room. If you're looking to protect the healthcare worker in the room, then providing them with clean air, right? Option number 3 is the only one that actually does that. Okay, so this is upper room UV, or I should say UVGI, but really we could talk about a whole bunch of different air treatment technologies here. This one for me is a bit frustrating. We know that UV, upper room UV works. They've been shown to be effective in removing aerosols. So it has a lot of endorsement in the clinical literature. This is definitely a tool that we could be using. But the application of these is not as simple as air change rate or filter efficiency. It doesn't work in percentages. It takes some real design. And frankly, our industry literature, both domestically and internationally, are not strong in terms of vendor independent application guides. So a lot of building engineers, including myself, don't know how to apply it. I can't make a statement on this slide about what the equivalent dilution factor is here because I just don't know. What I do know is that in order to kill viable particles, it needs to be strong enough, which is the variable of dosage. It needs exposure time, and it needs to be close enough, which is a variable of distance. For airborne particles, this should be great, right? Particles mixing around a room are going to pass in front of these UV lamps, and that'll kill it. For larger particles or droplets, it's pretty fair to deduce that these are not going to have a big effect because gravity moves things down, not up, and we need to get them up to where they can be killed. Okay, so now let's talk about negative pressure. I don't know when you're going to watch this, but the single biggest recommendation from HVAC people in March and April of 2020 was negative pressure, negative pressure, negative pressure. Negative pressure is for airborne suspended particles, and it is a strategy to decrease cross-contamination. If you have a room where airborne particles are being generated, that's the contaminated room. And so you use negative pressure to keep that contamination from crossing over into the next room, the space next door. Now, many negative pressure rooms also have quite a bit of air movement. The systems diagrammed here, in addition to being negative pressure, are also moving a good bit of air. So there's often a dilution effect that happens in addition to the negative pressure itself. But the negative pressure itself is only a cross-contamination strategy. And there seems to be some misunderstanding about that, or even some misinformation about that. It's worth repeating. Negative pressure can only prevent contaminants from leaving a room. Negative pressure does not do anything in the contaminated room. It prevents that contamination from spreading to other rooms. So for healthcare workers, if you're in the room, the negative pressure isn't doing you any good. If you're in the hallway, the negative pressure is a protective measure. Okay, so to review and sum up, we're looking at airborne or aerosols being less than 5 micrometers, droplets being larger than that. We treat those small particles as suspended in the air, but the droplets obey gravity. The bigger they are, the more they obey gravity. If we want to move particles on purpose, we need to have some speed in the air or some velocity. And for any particle that has an initial momentum from a breath or a cough or a sneeze, we need a good amount of velocity in order to capture it and move it. Probably the smartest thing to do, if you know where particles are being generated, is to remove them at their source with a local exhaust device. We can increase room air or outside air to dilute airborne particles, but not droplets, because the room air velocity is typically very low and it won't capture them. We can also use HEPA filters or UV systems to remove airborne particles, but again, not droplets, because we'd actually have to move that larger particle to the filter or to the light. Once we've cleaned air with a filter, my advice is not to waste it by throwing it outside. But then again, that's just me. And finally, we can use negative pressure to contain a contaminated space. At the risk of over repetition, negative pressure doesn't protect people in the room, it protects people outside the room in the next room. So I haven't said COVID-19 yet, and that was very deliberate. You can stop the video here if you don't want to hear any of my opinions. But I always like to remember, William Riley did the experiment that proved tuberculosis transmitted in the air. He put guinea pigs in cages and ventilated them with air from a tuberculosis ward. The experiment design was brilliant, and it's been repeated a whole lot since then. It's brilliant because it's deductive logic. It yields a specific logical conclusion. The patient had tuberculosis. The guinea pig never touched the patient. The guinea pig was not in the same room as the patient. The guinea pig could not have received a particle thrown out by a cough or a sneeze or an exhalation. The guinea pig sat in and breathed air, which came from the patient or from the patient's space. And so when that guinea pig tested positive for tuberculosis, which it did, the necessary conclusion of the experiment is that it got the tuberculosis from the air. That's the really terrifying prospect of an airborne disease. In my simple way of thinking, the terrifying thing about it is that it can turn a corner. It can start in room A and then move out into a hallway and then move into room B and infect somebody in room B. You don't have to be in the same room as the person you got the disease from. That's scary. It is like the Dustin Hoffman scene in the movie Outbreak. So far, as I'm recording this, and time will tell, COVID-19 has been talked about as a droplet transmitted disease. There's a ton of confusion in the terminology there, but because droplets exist in the air, but they're not necessarily aerosols. The WHO and the CDC have said that certain procedures like intubation or mechanical ventilation or even CPAP could produce aerosols. But even then, nobody, and I mean nobody that I've seen, has talked about this particular disease moving from one room into the next room and infecting somebody in the room next door. That is, to date, if you're not in the same room as the coronavirus patient, then you're not at risk from the air. You're at risk from everything they touch, but you're not at risk from the air. So obviously I'm recording this at the end of April 2020. It's still an active conversation. But I think there are some lessons that us HVAC people kind of need to learn from the event. First off, we need to use the right tools for the right job to the best extent possible. The HVAC industry jumped right out at the beginning of this thing and started saying negative pressure, negative pressure, negative pressure, negative pressure. As far as I can tell, negative pressure is a great tool for a different job. If this pandemic were an airborne pandemic, like a next generation measles or smallpox, that's exactly what we should be doing. That is a great tool. It's not necessarily the right tool here. Second, we need to use the best tools that we have. It blows my mind that in the early weeks of COVID-19, nobody was talking about that headboard ventilation. I didn't see the HVAC industry jump up about that. They weren't talking about local capture, and that's crazy because that is the single best thing that we could do. And it's a fraction of the cost of all these negative pressure room conversions. I know that in my job, we're going to be looking at lessons learned for extreme scenarios or disaster planning. I don't think we should necessarily assume that the next extreme scenario is going to be a droplet respiratory disease, but whether it's earthquakes or God forbid we do see a new measles, an airborne disease with an R0 of 10 or something, we need to have some better playbooks sort of standing by. I think we did not necessarily use our best tools for the right jobs that could have been done during this thing. And I hope that's a lesson that we can move and take forward. Thanks for watching if you made it this far, and have a good day.